Hey everyone, and welcome to another deep dive with us. Today we'll be taking a look at NASA's PUN-CH mission. It's all about the sun, specifically the corona and the solar wind. And we've got this really cool article from the Southwest Research Institute to help us break it all down. They're the masterminds behind PUN-CH. So what makes PUN-CH so special?
Well, PUN-CH is really going to be the first mission to study the corona and the solar wind together.
Yeah.
Like as one whole system. That's never been done before.
Yeah, and when you think about the corona, that kind of ghostly halo we see during an eclipse, it's always releasing this stream of charged particles, which is the solar wind, and it flows through the whole solar system. And sometimes things get pretty crazy out there. You get those space storms that can really affect us here on Earth.
Oh, yeah, for sure. And those storms, they can really mess with our tech, like power grids and even our satellites. So PUN-CH is really on a mission to help us understand those events and hopefully get a lot better at predicting them.
So it's kind of like, I don't know, trying to create a space weather forecast.
Yeah, exactly. But way more advanced than anything we have now. So PUN-CH is kind of like building a giant telescope in space. It's not one big instrument, though. It's actually 4 suitcase-sized satellites spread out way out in orbit. And they all work together, spanning a distance of like 8,000 miles.
Wow. 8,000 miles. That's like having a telescope the size of Earth. Can only imagine the detail we could get with that.
Yeah.
But how do they actually take pictures of something like the solar wind? It's not like we can just point a camera at it, is it?
It's definitely not that simple. Even though the solar wind is super powerful, it's actually unbelievably faint, like 1,000 times fainter than the Milky Way.
That's hard to even imagine. So how do they even begin to see something that faint?
So 3 of the PUN-CH satellites have these special instruments called wide field imagers, and they've got some really neat tricks to help them out. First, they use baffles, and these baffles can reduce the sun's glare by a factor of 10 million billion.
10 million billion. Whoa.
It's like comparing the mass of a human to the mass of a virus.
Oh, wow. That puts it into perspective. So, okay, they've figured out how to deal with the sun's glare. But what about the light from all the other stars? Doesn't that get in the way of the images too?
Oh, absolutely. But that's where some super clever processing techniques come in. So all the data from those wide field imagers gets sent back down to Earth. And then it goes through this really careful cleaning process. It actually removes over 99% of the light that's left over from the star field.
So they're essentially erasing the background stars to reveal that faint solar wind.
Exactly.
That's pretty amazing. So we've talked about those wide field imagers, but the article also mentions something called a narrow field imager. What does that one do?
Yeah, the narrow field imager, it's just as important. So it's on one of the PUN-CH satellites, and it basically acts like a coronagraph, which means it blocks the sun's brightest light. And that lets us see the corona directly. It's almost like we're creating an artificial eclipse. So we can study the corona even when there's no eclipse happening.
So the wide field imagers, they're focusing on catching the solar wind, while the narrow field imager gives us a clear view of the corona itself. It's like we're getting this really complete picture.
Exactly. And what's really cool is that PUN-CH is going to help us see the solar wind in 3D. So each spacecraft, it uses 3 polarizing filters and a regular camera to capture images every few minutes.
Polarizing filters, are those like the ones you find in sunglasses? The ones that help cut down on glare?
Yeah, you got it. But in this case, they're being used to analyze the light coming from the solar wind, which lets us figure out things like its speed and its density. And then by combining those images from all 4 satellites, scientists can actually track the 3D trajectory and speed of coronal mass ejections. Those are those massive bursts of plasma from the sun.
So PUN-CH isn't just about seeing the solar wind, it's about understanding how it moves and changes over time, which is really important for predicting space weather, right?
Absolutely. The instruments we have right now, they're pretty limited in how they can track these coronal mass ejections. They can really only measure the corona itself, but PUN-CH is going to completely change how we understand these bursts, how they travel through space.
It's like upgrading from a still photo of a hurricane to a live radar track. We can actually see it moving.
Exactly. And knowing the path and speed of these coronal mass ejections is really essential to improving our space weather forecasts. Imagine being able to predict solar storms accurately enough to know when to power down sensitive equipment, or reroute flights, or even postpone spacewalks. We could potentially save billions of dollars in countless lives.
Wow, that really puts things into perspective. So it's not just about protecting our tech out in space, it's about protecting people here on Earth too. This is incredible. Tell me more about these coronal mass ejections. What are they exactly, and why are they so dangerous?
Okay, so a coronal mass ejection, or a CME, It's basically a huge burst of plasma and magnetic field from the sun's corona. Imagine a billion tons of superheated gas, where electrons have been stripped from atoms,
Huh.
erupting from the sun's surface, and hurtling through space at millions of miles per hour. And this plasma carries this super strong magnetic field, which makes it a real threat to our tech.
A billion tons of superheated, electrically charged gas coming right at Earth. I can see why we'd want to be able to predict those.
Yeah, there's something to be reckoned with. And when a CME hits Earth, it can interact with our planet's magnetic field, and that causes a geomagnetic storm.
So how bad can the damage get, like worst case scenario?
Well, in a worst-case scenario, a powerful CME could cause huge electrical currents in our power grids, and that could lead to widespread blackouts. And they can also mess with radio communications, GPS signals, and even damage satellites.
That's not good. And I'm guessing the more we rely on technology, the more vulnerable we are to these events.
Exactly. Our world is so interconnected now, and we depend on space-based tech for so much. So understanding and predicting space weather is becoming absolutely critical, and that's where PONCH's unique 3D perspective is going to be so valuable.
It's like having a crystal ball for space weather. This mission could totally change how we understand the sun. What an exciting time for space exploration. But what about the technical side of things? What kind of tech makes all of this possible?
That's a great question, and it's something we'll definitely dive into right after a quick break. Stay with us.
Okay, so we're back. And I'm still thinking about PIONCH giving us a 3D view of the solar wind. That's pretty groundbreaking stuff. Can you walk me through how PIONCH actually creates this picture?
So it all comes down to perspective. Imagine trying to understand the shape and movement of a cloud if you only look at it from one angle. You're only going to get a limited view.
Right. You might miss details. Or get the speed wrong.
Exactly. That's why PUNCH uses 4 satellites. They're each positioned in different parts of Earth's orbit. So we get 4 different perspectives on the solar wind. It's kind of like having 4 eyes looking at the same thing from different angles.
4 different viewpoints. That's got to be really useful. How does that help create a more accurate picture?
Well, by combining those 4 viewpoints, scientists can build a 3D model of the solar wind. And that lets them see its structure, its density, and its speed in ways we've never been able to before, like taking a 3D X-ray of space weather.
A 3D X-ray. I like that analogy. So can you give me an example of how this kind of detail could help us actually predict space weather events?
Sure. Let's say there's a coronal mass ejection erupting from the sun. With PNCH's 3D view, we could pinpoint exactly where it's going and how fast, which means we could figure out if and when it might hit Earth and what the effects might be.
So instead of just knowing a CME is coming, we'd know its path and its impact. That's a game changer for protecting our technology and everything else out there.
It really is. And remember that huge blackout in the Northeast back in 2003? That was caused by a solar storm. PUNCH could help prevent those kinds of things from happening again.
That's good to know. Let's get back to those wide field imagers for a second. We talked about how they block sunlight and filter out starlight, but how do they actually capture an image of something like the solar wind?
So the key is how they use polarizing filters. Each wide field imager has 3 of them, and they only let light waves vibrating in certain directions pass through.
Kind of like polarized sunglasses.
Exactly. But they're much more sophisticated. By taking 3 pictures through those different filters and then comparing them to a 4th unpolarized image, scientists can figure out how the light from the solar wind has been scattered and polarized. And that tells them all sorts of things about its density, temperature, and speed.
It's amazing how they can get all that information out of light. And these images are taken every few minutes, right? So they can see the solar wind's movements in real time.
That's right. And remember, all of this is happening on 4 different satellites, spread out across a huge distance. They're constantly watching the sun, capturing the solar wind from all those different angles to build that 3D view.
It's like having a network of high-speed cameras, all pointed at the sun, catching the solar wind's every move. This is going to give us so much new information about space weather.
Absolutely. And once all that data gets back to Earth, powerful computers take over. They process it, filter out any noise, and put it all together into those amazing 3D images. It's like a giant cosmic jigsaw puzzle. But instead of a static picture, we get a dynamic, evolving view of the sun's influence on the solar system.
This is really incredible stuff. PANCH isn't just a science mission. It's about protecting our technology and making sure we have a safe future in space. This deep dive into space weather and the PNCH mission has been fascinating. Thanks for explaining it all.
My pleasure. It really shows how much we can learn and how important it is to keep exploring.
Absolutely. Now let's get into the specifics of the technology behind PUNCH. All right, we're back and ready to wrap things up with this awesome PUNCH mission. It's been so cool to learn about how it's going to totally change our understanding of space weather and protect our tech from those wild solar storms.
It really is a groundbreaking mission. So we've talked about what PUNCH is going to do and why it's so important, but now let's dig into how it all works, the technology behind it.
Sounds good to me. We've talked a lot about those wide field imagers, the ones that capture the super faint light from the outer corona and solar wind. Can you remind me how they actually managed to see something that elusive? Especially with all that glare from the sun.
Right. It's definitely not an easy thing to do.
Nope.
But those wide field imagers, they're equipped with this really clever combo of light blocking tech and some seriously advanced image processing.
We talked about the baffles that cut down the sun's glare. But what about the light from all the other stars? How do they deal with that?
Well, that's where the image processing comes in. All the data from the wide field imagers. It gets sent back to Earth, and then powerful computers take over. They analyze the images. They find the light from those background stars and remove it. And then they enhance that super faint signal from the solar wind. It's kind of like they're digitally erasing the stars to reveal the hidden patterns of the solar wind.
Wow, that's awesome. Like developing a photo in a dark room, but instead of chemicals, they're using algorithms and computing power.
That's a great way to put it.
Yeah.
And that processing is really crucial. It helps reveal all those tiny details about how the solar wind behaves.
So we've got those super sensitive cameras, the wide field imagers, capturing these images of the solar wind. But PUNCH is also going to give us a 3D view of it, right? How does that work?
Right, so for the 3D part, it all comes down to polarizing filters. Each wide field imager uses 3 different ones, kind of like the ones you find in polarized sunglasses.
Oh, okay. So they're like sunglasses for the spacecraft to help it see through the glare.
You got it. But they do more than just cut down the glare. Scientists can analyze the light that passes through those filters, and that tells them the direction and speed of the particles in the solar wind.
So it's not just seeing the solar wind, it's understanding how it's moving.
Exactly. And remember, PUNCH has 4 spacecraft, all in different spots in Earth's orbit. So they're capturing those polarized images from a bunch of different angles.
So it's like they have 4 different sets of eyes, each with its own pair of polarized sunglasses, all looking at the solar wind from different directions.
Exactly. And then by combining all those views, scientists can build this 3-dimensional model of the solar wind. It's like taking a 3D X-ray of space weather. You can see its structure and how it moves in amazing detail.
Okay, I think I'm getting it now. We've got the wide field imagers capturing the faint light, the polarizing filters showing us the direction and speed, and multiple spacecraft giving us different viewpoints. To create that 3D picture, that's some serious engineering and scientific know-how.
It really is. PUNCH shows how curious we are as humans and how much we want to explore the universe. And everything we learn from this mission could benefit us in so many ways.
Yeah, we've talked about how it can improve space weather forecasting, protect our satellites and power grids, even keep our astronauts safe. But it feels like we're just scratching the surface. What other doors could PUNCH open for us?
That's the exciting part. We're really just starting to see what's possible. But I think PUNCH could completely change how we understand the sun and how it affects our planet.
Bring on those aha moments. What kind of changes are we talking about?
Well, think about planetary atmospheres. Understanding the solar wind could help us figure out why Mars has such a thin atmosphere, or how Venus got so incredibly hot. The solar wind probably had something to do with how those planets turned out. And PUNCH could give us some really important clues.
So we could learn about the evolution of other planets by studying how the sun affects them.
Exactly, and it goes even further than that. Studying the solar wind could even tell us things about how stars form and how galaxies evolve.
Wow, that's incredible. We started with protecting our satellites, and now we're talking about the origins of stars and planets. It really shows you how everything is connected.
It really does. And that's why PUNCH is so exciting. It's not just about fixing problems we have now. It's about expanding our knowledge, exploring new horizons, and maybe even inspiring the next generation of scientists and explorers.
I totally agree. This deep dive into space weather and the PUNCH mission has been amazing. It reminds us that we're living in an incredible time for scientific discovery and that there's so much more to learn.
Couldn't have said it better myself. Keep looking up and keep exploring the wonders of our universe.
Thanks for joining us on the deep dive, everyone. We'll catch you next time for another exciting journey into the world of science and tech.